today we're going to do probability, and we're going to look at just some basic probability that you've maybe seen and done before, but also try to build into using some of those combinations and permutation content that we learned yesterday. And we have to kind of build some background for it so that we kind of all have a level playing field of knowledge about the types of things that we're going to look at for probability. One of them is rolling dice. Invariably, a lot of probability does revolve around gambling, and so dice, cards, those are some of the things that we use as examples of how to find probability. So, rolling dice. We all know that when you roll a dice, there's 6 options. We're going to dig into something a little deeper, is like when you're rolling 2 dice. Ultimately, it's kind of like the fundamental counting principle. If you're going to roll 2 dice, you have 6 options for the first one times 6 options for the second dice, and therefore there are 36 different ways this could play out. And this chart kind of helps you visualize that of how that might play out. It is important to understand that when you're rolling those dice, those are considered 2 different dice. So rolling a 3 on one and a 1 on the other would be considered a different outcome than a 1 on the first and a 3 on the second. Those are different. And you can kind of see that right here. Here's a 3-1. Here's a 1-3. That's a different roll. All right, so here's kind of the breakdown of all the different ways that can happen. One of the things that is helpful when you see it in this chart is often when you're rolling dice, you're looking at the sum of the dice. So let's look at everywhere that the sum of the dice is, let's say 6. Well, that's going to happen on a 1-5 and a 2-4, a 3-3, 4-2, 5-1. And so anytime you're getting the sum of something, it always will fall along a diagonal. Here's an example of rolling a 10. Well, you can get that with a 4 and a 6, a 5 and a 5, or a 6 and a 4. So that's helpful if you'll recognize that's the way this lays out. Another example would be playing cards. And if you're not familiar with cards, here's kind of the cheat sheet for it that you may have to come back and look at every once in a while until you get used to it. There are 52 cards in a deck. We don't typically deal with the jokers. If we're dealing with the jokers, now there's 20 or 54, but we're going to always deal with 52 cards. There's 13 of each suit. A suit are these different, a club, spade, hearts, diamonds, those are suits. And then these are the numbers that you have all the way through in each one of these. So it's basically 2 through, well, here's 10, 11, 12, 13, 14, except we didn't have a 1. So this is 13 different options times 4 equals your 52. The order that you get cards does not matter. We mentioned that a little bit yesterday, because as soon as you are dealt cards, you typically are rearranging them in your hand anyway. And when we're pulling multiple cards, we will typically default to without replacement. In other words, if you're dealt a card, you hang on to that. It's not like they take it and they put it back in the deck before they deal another card. That's called without replacement. If you ever see the term with replacement, it means they'll give you a card, take it back before they deal another card. Okay, and then the third scenario is the lottery. The lottery, like for instance, the Powerball, Mega Millions, whatever the lottery might be, when you are picking those numbers, the numbers that you are picking them, okay, and of course there's different types of lottery drawings, but we're going to stick with like the Powerball and the Mega Millions, kind of the main ones, where the order that you pick those numbers doesn't matter at all. You pick your 5 numbers, and you're just hoping those 5 numbers come up. Doesn't matter the order they come up. They also don't repeat. And really the way it works, if you ever like played bingo where they pull a ping pong ball out, it has the B7 or whatever. Well, okay, the Powerball kind of works the same way. There's like this ping pong ball machine, and it's shooting out numbers, but each number is only in there once. So once that number comes out, it cannot be redrawn. Which means since there's no repeat and order doesn't matter, anytime we're dealing with a lottery, we need to be using combinations. That's the only one where order does not matter. Okay, and then the other thing, since we're now talking about probability, the number of successes for winning the jackpot is 1. There is only one set of winning numbers. So keep that in mind as we move forward. Probability in general is found by taking the number of successes over the total possible. This is sort of our notation for probability. It's the probability of some event occurring. You take the number of successes that are out there over the total possible. This total possible right here, that's where our combinations are coming into play, because that's what we were finding yesterday. What's the total number of ways something can happen? That's now going to be our denominator. All right, probability will always fall somewhere between 0 and 1. 0 is an impossibility, a 1 is a guarantee, anything in between. We typically will write probability as a fraction or as a decimal, not usually as a percent, not for what we're doing. So let's practice a few basic ones where we don't have to do combinations yet, but just looking at this chart of rolling dice, what's the probability of rolling a 7? Well, remember what I told you, those are always along a diagonal. So here's a 7, all the way through here. There are 6 ways that we can get a 7. So that means there are 6 successes out of a total of 36 possibilities. Be sure to always reduce that. If it comes out nice like a fraction, we'll go ahead and leave that fraction. We'll shift to a decimal when we start getting kind of messier numbers. All right, the probability of rolling a 3. Okay, well, same deal. Here's your 3s. Oops, not there. Here's a 3, here's a 3. Now, when we say a probability of a 3, we're always talking about the sum of the dice on these. And so there's 2 out of 36 reduces to 1/18. Okay, let's get a little fancier. What's the probability that it's greater than or equal to 10? All right, so that means a 10 or an 11 or a 12. So here are my 10s, here are my 11s, and here's my 12. So there's 6 ways of doing that. So again, we have that 6 out of 36, which reduces to 1/6. The next thing I want to talk about is the complement of an event. Complement events are like opposite events. It's like the probability of something happening and versus the probability of something not happening. And you can see this seems like it's really grayed out on this screen. I hope it stands out better in your notes. But the probability of some event occurring plus the probability that event does not occur. Do you see that little apostrophe, little hash mark prime number there? Or that means not happening. The probability of something not happening. So the probability that does happen plus the probability it doesn't happen will always equal 1, because remember, 1 is something guaranteed. And something is either going to happen or not happen, one or the other. But these two should add up to equal 1. Now, that's not usually the way we play it. We usually play it like this, where the probability of something not happening is 1 minus the probability it does happen. That's just rearranging this equation. And you could go the other way as well. The probability of an event happening would be 1 minus the probability it doesn't happen. So this is a method that's sometimes easier to count up the way the probability that it doesn't happen than the probability that it does happen. This is often used when we talk about what's the probability that at least one, well, at least one means, well, 1 or 2 or 3 or 4 successes. It's maybe easier to do the opposite of at least 1, would be the 1 minus the probability none of successes. You have no successes. So keep that in mind. I want to go back to this dice rolling. So the probability of it not being a 7 when I roll 2 dice, and again, that's the sum of a 7. Well, there's a lot on this chart that are not 7s. So rather than counting up all the ones that are not 7, I'm just going to do 1 minus the probability that it is a 7. And if you recall, these are the kind of the same questions as earlier, but I'm now putting a not on it. So this is 1 minus 1/6, because that's what we said the probability of a 7 was. So that's actually going to end up being 5/6 probability. So easier to come up with what it is than what it isn't. So we use this little complement property. So the probability that you roll a sum other than a 3. Okay, again, I would rather do 1 minus the probability that it is a 3. And that would be every other option then. We had said that that was 1/18th. So I guess I should change that to 1 minus 1/18th, which is going to be 17/18ths. Okay, let's try the last one. The opposite of greater than or equal to 10, which is what I did last time. Now I want the probability that it's less than 10. So I only can put an or equal to on one or the other of them. So the last one had an or equal to, so this one does not. So 1 minus the probability that it is greater than or equal to 10. So that's 1 minus 1/6, again, coming from the previous slide. So we're back to 5/6 is the probability of that. A lot of the time you hear that term odds, and it's like we use that interchangeably. What are the odds of something happening, or what is the probability of something happening? Like it means the same thing. And I guess ultimately you are just like looking at how likely is something to happen. But the way we write odds is definitely different than how we write probability. Probability is the successes compared to the total possible, whereas odds are the successes compared to the failures. And often you will see odds written with a colon rather than as a fraction, more often with this colon. But you're still dealing with successes, failures, total. I guess it would make sense. Well, let me go ahead and go to the next slide here. When you look at the number of successes versus the number of failures, well, these two are always going to add up to a total. So the total will be the successes and the failures added together. So let's do some converting between probability and odds. When I say what's the the probability of getting a 6 on a single die, so you're just die is singular for dice, if you didn't know that. It's not really a typo there. But when I write 1/6, 1 are the successes, the number of successes that there are in there. 6 is the total. Because we're talking about probability, it's successes over total, which must mean then that there are 5 failures, which is the 1, 2, 3, 4, and 5. So let's look at when we talk about successes. I guess I don't know why I wrote that up there. Sorry. Successes are 1. Total is 6, which makes failures be 5. So if that's the case, the odds, remember, odds are successes to failures. So for rolling a 6, that would be a 1 to 5. Those are the odds. 1 time you're going to have a success, 5 times you're going to have a failure. If you're looking at the odds against rolling a 6, then that flip-flops. That's going to be a 5 to 1 because there's 5 failures, 1 success, and those are the odds against having a 6. Now, I've done this long enough that I know that it seems like a simple concept, and yet people still continue to goof it up. So don't be afraid to just jot a few things down. The probability of making a free throw is 7 to 10. That means 7 is a success, 10 is the total, which means failures would be a 3. So don't be afraid to jot that down so that you get the next part right. What are the odds for making a shot? Odds are successes to failures. And the odds for missing it, well, that's the opposite. So then you would flip-flop your odds. That's a 3 to 7. Okay, let's go the other way. What if they give you odds and you want to go to probability? So the odds of winning the game are 2 to 1. Odds are successes to failures, which means our total would have to be a 3. So the probability that you win, well, the odds of winning were 2, that's a success, that's winning, so the probability would be 2/3. The probability of losing would be that failure would be that one number over the total of 3. So we'll do some converting between probability and odds and understanding that those don't really mean the exact same thing and understanding how to write those. Okay, so we've been looking at a lot of different topics. I feel like I'm flying through these notes, but it's all a lot of just, what if this happens? What if that happens? What if this happens? And so here's another scenario. What if you are looking at a situation where you want this or this to happen? You have 2 options here. Either one of them you would consider a success. So the probability of A or B happening, those are some events. That word or indicates you should always add. Or means add. So typically what you'll do, the probability of A or B occurring, whatever these events might be, you're just going to take the probability of A happening plus the probability of B happening, add it together. That's the probability of one or the other happening. Now that's the rule, the formula we would use if these events are called mutually exclusive. That means they're totally different things. They can't happen at the same time, like getting an ace or getting a king. Those are 2 totally different things. Now, if you happen to be looking at things that are not mutually exclusive, so the probability of A or B, you still take A plus the probability of B, but you have to subtract out the probability that both occurred. So right here, like the probability of an ace getting, you're just going to pull one card out of the deck, and the probability that it's an ace or that it's a diamond. Okay, the reason these are not mutually exclusive is because the ace could be a diamond. So those could happen at the same time. And what that would mean is that you would be counting the ace of diamonds in this category. You would be counting it again in this category, which means it got counted twice. So you have to subtract out anything that got over counted. I call that overlap. It got double counted, so you have to subtract that out. I feel like these problems seem to be the most commonly missed on the test. And the problem with missing these on the test is that there's not a lot of partial credit. You either know what you're doing here or you don't. And so if you miss it, it's just boom, -1. And there's no partial credit. So let's go through this again. The probability of an ace or a king. Okay, an ace. You're doing probability, so that's successes over total. There are 4 aces in the deck out of 52 total. Or tells me to add. I also would consider a king being a success. So there's 4 kings out of 52, which gets me 8 out of 52. Now, we'll do enough of this card stuff that you'll start to learn that 4 out of 52 reduces to 1/13. So this is really a 1/13 plus a 1/13. So this I know is going to reduce to 2/13. That's the probability. And that is because when you pull a single card from a deck, it can't be an ace and a king at the same time. Now, in this next example, though, pulling an ace or a diamond, that could be the same thing. So we do the probability of the ace plus the probability of the diamond. Remember, there's 4 suits, 13 of each one of them. So there's 13 diamonds in the deck. And then I subtract out anything that might have gotten double counted, which really in this example is only the ace of diamonds. So I have to subtract out 1 card out of 52 that got double counted. And that ends up being 16 out of 52. 4 goes into both of those. So that ends up in being a 4/13 probability. Okay, now the next ones are new ones. I had already talked about those on the previous slide. Let's try this next one. Probability of getting a spade or a face card. Okay, probability of a spade is 13 out of 52. Plus, okay, face cards are all the cards that have a face. that means it's a jack, queen, king. That's it. Jack, king, queen. But, so there's those three, but they're in all four suits. So that means there's a total of 12 face cards in the deck. So 12 out of 52. But then I'm going to subtract any overlap that might have happened, which would have been the face cards that were also spades. And there are three of those. The ace of spades. I'm sorry, not the ace. People ask me, is an ace a face card? It is not. There's not a face on it. So it's the king of spades, the queen of spades, and the jack of spades. Okay, so that ends up getting us a 22 out of 52. Those are both even, so we could at least break it down to that. Okay, what about the probability that it's not a spade or a face card? Okay, well, that's the complement of the question I just asked you. It's the opposite. So the opposite, I'm just going to do 1 minus the probability that it did happen. And I just learned that the probability that did happen is 11 over 26. So remember, you're just going to take this and turn it into 26 over 26, which gets us a 15 over 26, and I don't think that's going to reduce for us. All right, let's change that to the odds that it is a spade or a face card. All right, so this is referring back to this part C. We know that 11 are successes, 26 are total, which means failures would have to be 15. So if I'm doing odds that it's one or the other, I'm going to go successes to failures. Now, odds do reduce the same way probability can. Now, 11 to 15 is not going to reduce, but let's say it was 5 to 15. I would expect you to reduce that to a 1 to 3. Here's the next scenario. Instead of an or, what if it's an and? What if I want some event to happen and another event to happen right after that or with that? An example of that would be if you were pulling 2 cards from the deck now. All right, so I want to get an ace and then a king. And then it says with replacement. Remember, that's rare. We don't typically put the card back in there, but this is an example where I'm going to. So I take the probability that it's an ace. Oh, you know what I don't have on this slide that I should have on this slide? Is that and means multiply. You need to write that down. Or means add, and means multiply. So I want an ace and a king. So the probability of an ace is 4 out of 52. And now I'm going to multiply a king. Now I did replace that ace that I got in first, so now I put it back in. There's going to be 4 kings in the deck and 52 cards. Now you're going to, like I said, want to learn to be reducing these. 4 out of 52 is going to be a 1/13 times another 1/13, which is 1 over 169 probability. Okay, let's mix it up a little bit. Let's say this time I want an ace and then follow it up with a king, but this time I'm going to do it without replacement. Well, that does not change the probability that I get an ace to start with. That's still 4 out of 52. I could write that as a 1 out of 13. I should have, but I didn't, so I'm going to keep going. All right, now I want a king, but this time the ace is staying out of the deck. Well, that doesn't affect the fact that there's still 4 kings sitting in the deck, but there are not 52 cards anymore. There are only 51 cards. Okay, so now let's do some reducing. This is 1 out of 13. I'm afraid 4 out of 51 does not reduce. So let me grab my calculator here. 13 times 51 is 663. So I end up with a 4 out of 663. We're starting to get to the point where we might go decimal when it starts getting that ugly. But if you go decimal, I was just going to type that in real quick. Don't be too anxious to round. Like that ends up being 0.006033. I don't know. I guess you could go 0.006 because the next digit is a 0 and it's a kind of a clean cutoff. I would never go less than 3 decimal places, though, when you're doing probability as a decimal. Okay, I'm going to get fancier. Now I'm going to pull 4 cards from the deck. So here's what I want to have happen. I want to pull a spade, a club, a diamond, and a heart in that order without replacement. Okay, so without replacement, I guess I'm afraid I'm gonna run short of space. So right here, I'm gonna just sneak it right under here. The probability of getting a spade. Remember, there are 13 of each one of these suits. So there are 13 spades out of a total of 52 cards. And this is an and situation. I want to get the spade and then the club and then the diamond and then the heart. So I'm going to be multiplying. Now let's think. I did not replace that first card. I'm keeping the spade that I have. Now I want to know the probability of getting a club. Well, the fact that I got a spade does not reduce the number of clubs in there. There are still 13 clubs, but it does reduce the total number of cards. There are only 51 cards in the deck. And now I'm going to get a diamond. Again, so far I've just got a spade and a club in my hand. There are still 13 diamonds in the deck to pull. Out of, now there's only 50 cards in the deck. And for hearts, there's still 13, but there's only 49 cards in the deck. Okay, so now I know that this is going to end up being a pretty dang ugly fraction. So this is an example where I might just go straight to the decimal. Now you can take each one of those fractions times themselves. I tend to be more inclined to just multiply across the top and then multiply across the bottom. And then I will just divide those two numbers. Okay, let's see how unlikely this is to happen. I'm going to guess pretty unlikely. So when I divide that out, I get 0.00, and I told you never go less than 3, even if these are getting something other than zeros here. I've got a 0.00. It's a 439, so I feel like a 44 might be a good place to cut that off. So yeah, not very likely. Okay, let's look at this next example. Let's try to get a flush, the probability of getting a flush. And a flush is a nice poker hand where you're getting all the same suit. Now, this is a 4-card hand, not a 5-card or 7 or whatever poker oftentimes is, but 4 cards, all the same suit. That's what I want to have happen. Okay, so what's the probability that you get a success on that first card? Well, the thing is I don't care what the first card is. It could be a heart, it could be a diamond, it doesn't matter to me. So there are 52 successes out of 52 cards. That's a probability of 1. That would reduce to 1 because anything I pick is a success, probability of 1. But once that has happened, then, okay, so to be honest, now that we've talked about it, I'm just going to write it as a 1. Now, whatever it was that one is, the rest of them have to be the same thing. So let's pretend it was a heart. Well, I've got 1 heart in my hand. How many hearts are left in the deck? 12 out of, and again, we're sticking with the without replacement here. Okay, so that means there are only 51 cards left in the deck. Now I want there to be another heart. Well, now I have 2 of the 13, so that means only 11 are left out of 50. And then I have 1 more round to go. There's 10 hearts out of 49. Okay. I went ahead and did the math on this one ahead of time, or just now did it, so that we could keep moving forward. I have a probability on this one of 0.011 is what that would round to, 0.011. Now, this probability is very important because if you're playing, for instance, poker, whichever hand is the least likely to happen is the winning hand. So these probabilities, the probability of getting a flush versus a straight or a pair or whatever, this probability dictates what the winning hand is. That's why this is important in gambling, I guess. Things that are rare or unlikely win you more money. Okay, so let's move on to a different type of situation. Let's look at a Venn diagram. It's another way of kind of looking at probability, but you have to organize the data first into this Venn diagram to figure out kind of what that probability might be. So it says here, in a group of 27 students, 13 of them are in a biology class, 18 of them are in an algebra class, 7 of them are in both a biology and an algebra class. If a student is chosen at random, what's each probability? All right, let's fill in our numbers. Now, it might be tempting to say that there are 13 in biology and 18 in algebra. I used A for algebra, B for biology, and then 7 in both. But if you add this up, that does not add up to 27 students. That is not what this means. It means that there are 13 students in biology, but of those 13 that are here, 7 of them happen to also be in the algebra. So I can't put 13 here. I have to have 13 total in the B circle, which means really there's only 6 that are just in biology, 7 that happen to be in biology, but also in algebra, but there's my 13. So same thing here. I don't have 18 in algebra. I have 18 in the algebra circle. 7 are already accounted for here, which means there are an 11 that are just in algebra. Now, I said that wrong earlier when I said, hey, this doesn't add up to 27. Well, this doesn't add up to 27 either. But this was the way we were supposed to do it. What does this add up to? Yeah, this actually adds up to 24, and there are supposed to be 27 total. Where do you think my missing 3 students are? Yeah, they are outside the Venn diagram. They are not in algebra or biology. So I put the 3 on the outside to accommodate that situation. So let's do some probabilities. What's the probability a student is in both biology and algebra? Okay, that's that success. That's 7 students out of our total of 27 students. What's the probability they are only in biology? So they're in the biology circle, but not in the overlap. So that's my 6 out of 27. I should have had an extra question asking about those 3 that aren't in either, but just be aware that there can be some that fall outside of the Venn diagram. All right, time to put it all together and use all of that stuff that I've talked about is all fair game. It says you pull a card from a standard deck. What's the probability that it is a red face card? Okay, so it's kind of like going back, thinking through all the things we've talked about. Which scenario was this, and how do we do it? Okay, we're only pulling 1 card, so there is only 1 probability that I write. How many successes are there? How many red face cards? There's 3. No, there's not. I take it back. There's 6. Because you have diamonds and you have hearts. And there are 3 face cards of each of those. So 6 total red face cards out of 52. All right, go ahead and reduce that. to 3 out of 26. Okay, let's look at this one. Stepping away from the cards here. If a batter has a .275 batting average, they usually just say that's a 275 batting average. Okay, what are the odds that she gets a hit the next time at bat? Okay, a .275 is really a 275 out of 1,000. That's what that would look like. And that would be a probability. That's the probability they're hitting. They hit 275 times out of 1,000. Now, the first thing I would want to do with this probability is go ahead and reduce it. I know that at least 25, I know, is going to go into both of those. So I'm going to do a 275, divide by the 25. All right, that's an 11. And 25 is going to go into 1,000. 40 times. Now, this is a probability. This is successes to total. If they want to know what the odds are, that means we've got to go back and figure out what the failures are. So 11 successes out of 40 means there's 29 failures. Okay, so down here out of the way, I write, oh yeah, there's 29 failures. That means my odds of getting a hit are 11 to 29. And it helps that I reduced earlier. It saves me from having to reduce at this stage here. All right, let's take a look at this one. It says the probability that a 30-year-old is married is 0.29, and the probability that a 30-year-old owns a home is 0.22, and the probability that a 30-year-old is married and a homeowner is 0.12. All right, this seems very much like that Venn diagram problem that we did, and we could probably do it as a Venn diagram, but I wouldn't have to, because the other thing that seems to jump out at me on this is that whole mutually exclusive thing. Like, can you be married and a homeowner at the same time? Yes, you can be. And so that's that thing where you subtract the overlap, which is really what we were kind of doing when we were doing that Venn diagram. So I'm going to set this up. Now, I guess it is worth mentioning. It says, what's the probability that a 30-year-old is neither married nor a homeowner? Okay, that's really a complement of the probability that they're one or the other. So I feel like I'm tying a lot of things into this one problem. So I'm going to go with the probability that they are married or a homeowner minus the overlap, a married homeowner. Okay, so the probability of married is 0.29. Probability homeowner is 0.22, but I have to subtract the probability that they're both 0.12 because those people got counted twice, so we got to subtract those out. So what's that end up getting us? I think that's 0.39. Okay, now that's not really what they asked though. This is the probability that they are married or a homeowner. I want the probability they are not married or a homeowner. So that's going to be 1 minus the 0.39, which is 0.61. And that answers the actual question. All right, we're finally getting to it. As promised, we're going to use combinations to help us figure out how many ways can it happen? How many success, or not how many successes, but how many total is there? What's that denominator need to be? Let's look at this problem. It says, what is the probability that you correctly pick the Powerball numbers? Now the Powerball, because I know you don't know this, you have to get 5 numbers from a set of 1 to 69. And then you also have to select the Powerball number 1 to 26. Remember what we've said about the lottery way back at the very beginning of this notes that was quite a while back, is that The order you pick the numbers doesn't matter. I also mentioned that there is only one successful jackpot winner here. So looking at this, when I'm doing probability, I'm going to do the probability that you get all of those. They're usually like white balls, and then the Powerball is a red one. So let's talk about the white balls. I got to pick 5 numbers from a set of 69. So this is combinations. There's 69 numbers, and I have to pick 5 of them. Now that's the total number of ways it could happen. A success is just one. There's only one successful lottery ticket or set of lottery numbers. But I don't just have to do this. It's like this, and I also have to do it for the Powerball. So there's still only one successful Powerball. It's going to be combinations of, there's 26 numbers, and I have to pick one. Okay, that's how you do. Let's look at how rare this is. What the likelihood of winning. I bet you my calculator won't even show it. Now, I do remember from Pascal's triangle that 26 choose 1 is really just a 26. So that makes life a little bit easier. I don't have my graphing calculator, so I grabbed the scientific calculator, which may not do this. Let's see what we get. Oh, it did. It wasn't that rare. Okay. It wasn't as bad as I thought. Okay. And then whatever that number is, looks like it's about 11 million. I have to take my 11 million number times the 26. I'm just doing the denominator here. And I've got, okay, so numerator is just going to be a 1. And my denominator is 292,201,338. So not very likely going to win that Powerball. We made it. It's the last slide. Okay. So still using combinations. If the math department has 6 women and 5 men, what's the probability that 4 are chosen to go to a conference? And it ends up being 3 women and 1 man. All right. This is going to be a little bit more complex than all those other stuff we've been doing, because you're going to use combinations. Yes, because I'm choosing people. I don't care the order that I pick them. I'm just getting these women. I'm getting men. I have to look at a success, and I have to look at a total, and both scenarios are going to end up being end up being combinations. So let's start with, I'm going to do this over here on the side. Let's start with the denominator for no particular reason. Here we go. Combinations of. I'm just going to grab people, and they're going to, specifically, I'm going to grab 4 to go to a conference. All right. How many people are in the department? 11. And I'm going to pick 4 of them to go to the conference. That's how many ways it might play out. Now, a success for us, this is the numerator, would be 2 different combinations, because I've got to look at the female and then also look at the male. And it's a this and this happening, so I have to do a times on this. For the women, let's see, there are 6 women, and we want to end up with 3 of them. There are 5 men, and I want to end up with 1 of them. That's what I would do to figure out what the probability that it plays out exactly like this. Now, it is nice if you start remembering from Pascal's triangle some of these things, like a 5 choose 1 is just a 5. It's so much easier than having to keep typing things into that probability menu, because I feel like it's kind of buried sometimes in that calculator. So the 6 choose 3 happens to be a 20. 20 times 5 is a 100. That's nice. And then the 11 choose 4. Okay, that's 330. So I'm going to end up with 100 over 330 And I don't know, we probably would just go decimal on that. Well, I don't know, it could reduce. It really isn't bad at all. You could say it's 10/33. Or we could go ahead and do the division and see what it is. It's a point. And this is really approximately because it does not come out exact, 0.303. All right, so this next one, back to the cards here. Suppose that 5 cards are drawn from a standard deck. What's the probability that you draw 3 kings and 2 jacks? Okay, so that would be called a full house. When you have 3 of one kind and 2 of another like this, that's a full house. So we want this very specific full house. We want the 3 kings and the 2 jacks to happen. And I'm just getting 5 cards. I'm going to think that this is probably unlikely that I pick 5 cards and this is exactly what I get. But let's see. This is actually very, very similar to the math department going to a conference. We start with our denominator. How many cards are there? 52. How many am I choosing? 5. And then the way I want this to play out for a success is looking, let's start with the kings. A success would be to get 3 kings. Well, how many kings are there? 4. And I want to get 3 of them. And I also have to do the jacks. How many jacks are there? 4. How many of those do I want? 2. All right. So maybe you remember from Pascal's triangle that a 4 choose 3 is really the same thing as a 4 choose 1. So I know that's a 4. And a 4 choose 2 happens to be a 6. You may not remember that. That's okay. You can type it in. But altogether, I can see my numerator is going to be a 24 there. And then I don't know the other one, so I will type that one in. So 52 choose 5 gets me this big old number. And if I go ahead and I divide that out to get a decimal on this one. Oh, Lordy. Okay. So I said you can't go less than 3 decimal places, but here's what I'm looking at. 0.0000923. 4. I'll throw that in there too. Okay, so I can't go 3 decimal places because that would have been a 0, but there is a likelihood. It's just very, very slim likelihood that's the hand that I draw. All right, keep these notes out handy as you're doing your homework because there's a lot of different things we've covered, but you should find something in your notes that matches the questions that you're getting on your homework. So use them wisely. Good luck.